yeah, I think that's it. What I want to do today is take the next step in learning how to simulate groundwater flow. And we'll do that by putting together the concepts that we've been looking at so far. And we'll use those concepts to develop an equation that we say will govern the hydraulic head distribution within an aquifer. And we'll solve that equation, and that'll give us a way to describe the distribution of the hydraulic head. We'll solve that equation over the next few weeks several different ways. So we'll first of all solve it in analytically. So we'll get basically just another equation. We'll get like a just a little algebraic equation. You can plug in some numbers and get some back and plot it easily in Excel. So that'll be the analytic approach. And what we'll see is we can do some simple problems that way. It'll be nice because we'll get some simple equations that can be plotted, and we can analyze those equations in some fairly straightforward ways. But it'll be limited in the kind of the depth or the level of complexity that we can address with that kind of approach. So we'll show you a way to solve the groundwater equation graphically. So we can go then to 2 dimensions and solve some more interesting problems. And it just is involving a pencil and an eraser. So that'll be in a few days. And I want you to bring a pencil and a decent size eraser, because you're gonna have to erase off stuff as you draw it. That's a technique called flow nets. Now allow us to visualize what the flow system looks like. But then for really practical problems, that's the flow nets will help. But really the way that we do it these days for practical problems is with numerical model. And we have a site license for a numerical model that is a professional grade groundwater modeling package that many companies use in consulting. And so we'll get an introduction to using that package. It's big package, does many things. We'll use a small piece of it, but nevertheless, it'll be an introduction to solving groundwater flow problems. Okay, so that's where we're headed over the next few days. What we need to do is start off with some concepts. So the basic question here is, this is the cross section, that we started with on day 1. Question is, well, what's happening here and how do we predict it? So in order to predict, we need to have some mathematical approach to telling what these flows are. What direction is it going and how fast is it flowing? So the way to do that is in reality, I mean, this is a simplification of reality. And reality, of course, is much more complicated than this. But even this is fairly complicated because we've got a lot going on. We've got some evaporation from trees and flow in the vadose zone. We've got some soil here that causes flow to go down slope and then flow in the aquifer. So the strategy to doing simulations is going to be to simplify reality. And at first, we want to simplify it as much as we can and not throw the baby out with the bathwater, right? We want to simplify it down so that it's as simple as we can get it, but still has the essence of the problem. And then we'll solve that. And then if that helps, then good. And then we can, once we understand how to do that, we can add in a little more complexity and solve that and build on the insights that we have from the first step. Okay, so that's going to be the strategy. Ultimately, we can then build it up to be fairly complex. So one of the things we can do to simplify this is realize that, you know, when I drew this, I used vertical exaggeration because I wanted to show what's going on here, but really around here from the groundwater divide to the stream is about 500 meters, and the thickness of the saturated zone might be 10 meters. Okay, so this has a lot of vertical exaggeration, and if we take out the vertical exaggeration, it looks actually more like that. But if I drew it like that, you know, you can't really see what's going on. So that's why I did it. But if we're going to simulate it, we need to then be cognizant of what reality is. And reality is that the groundwater is a thin layer. And if we look at the flow paths here, they're curving quite a bit. But here, when we take out that vertical exaggeration, they're much straighter. And there still is a vertical component, but they're much straighter. And then we can consider ignoring the vertical component and just analyze the horizontal component as a first cut. So what I'm going to say is that this situation here, where I've got this thin layer, mostly vertical flow, and then there's this recharge that's coming in. So what I'm going to say is that I'm going to replace that with this. And what I've done here is I put in this confining layer, and what that's going to allow me to do is to say that the flow that I'm interested in is in this layer here. And there's a recharge through this confining layer. So there's flow going into the aquifer through the confining layer, but I'm not gonna, I don't have to consider the flow up here in this water table. We have this curved surface. We'll get to that next, but for now, I want to simplify it to just have this layer where the flow is occurring that will be of uniform thickness, and I'll call it B. Okay, so this is the conceptual model. That's what we typically call it. It's showing the essential aspects of the problem, and that includes recharge coming in, and we'll assume that the recharge is just uniformly distributed. And then there was a stream over here, and the stream is cutting all the way through the aquifer. And you know, that usually doesn't happen. Usually streams, I don't know if you ever plot a stream in cross section, they're really thin relative to their width. So the streams really are going to be sitting, you know, on top of an aquifer, say. But in this case, we're going to assume that it cuts all the way through, just to get started. Okay, so given this, there'll be a divide right here. Okay. And so the flow is going to be 0 right here. And as we move along in this direction, we'll accumulate more and more recharge. So the flow in this direction is going to increase. And it'll be maximum here and 0 at this end. Okay, so that's how we're going to conceptualize the cross section that we started with. Okay, so we want to simulate what the hydraulic head is and what the flux is in that scenario. So in order to do the simulation, we need to have some kind of a governing equation. In order to get that, we're gonna basically base that governing equation on rules that we feel are going to apply, that have to apply to the the problem at hand. So pose the question here, what are the rules that are going to apply to our problem? One of the rules would be a law, obey the law. So what would the law be? This is the flow through an aquifer. So what do you think it needs to do?
Conservation of mass.
Conservation of mass would be a law, right? We talked about that, I think, on the first day. We call it a water balance. So seems like it better do that. Black. Third. So we had a version of the mass conservation that we recognized as the water balance. We said it was the volume going in is the volume going out plus the change in volume stored. So we started off with that, and that seems like this is just from basic physics, so that better apply. So that's one rule, sure. What about another rule? Any rules back here? Anybody? Rules? Law?
High energy to low energy.
High energy to low energy. What's the law? Darcy, yeah. So I mean, better have Darcy's law involved here. Okay. So these are the physical principles, and then these are kind of governing like what's happening in a conceptual way. If we want to solve that particular problem, we have to have these kind of tailored specifically to the problem at hand. So we need to have it apply to the well, let's call it the field problem. Field, well, the field case, and then we're representing the field case with the conceptual model. So it has to apply to that example that we showed on the sketch or on the previous slide. And one of the things that we're going to need to have it do is it's going to have the right properties. So we talked about the hydraulic conductivity, storativity, specific storage, those things. So our field case will have certain properties, and our simulation better have those properties, better consider that. And another thing that it will need to do is, well, let's call it geometry. So like the thickness, the length of the aquifer. And there'll be another aspect that will be applying it to the field case that will be the boundary conditions. So we're going to have a region. The way it's going to work, we'll have some region, and these things are going to apply within the region, and the geometry will tell us what this thing looked like, this square box. The properties say what's inside, but then we're going to have to say what's happening at the boundary. Okay, this stuff is inside, boundary conditions are what happens around the edge. Okay, so if we can do that, those are the rules, and if we can do that, then I think we're gonna be able to proceed. There's boundary conditions parameters, and also that would include geometry. Okay. So we're gonna do the balance. Conservation of mass with what about? So the way we did this before was we took, well, the way we did it before, we had a control volume and we had in and out and change in storage. So the control volume with our approach before was kind of a large scale. We would do it over the whole Vado zone or the whole aquifer or the whole watershed, that kind of thing. So we could do it over the whole aquifer. But the problem is that the way with this volume balance approach, you find out what's happening on average within the control volume. But you can't really get in and look and see any details within the control volume. So if we did the balance on this, we could find like what the overall ins and outs are, but we couldn't find out what the distribution looks like. We want to see like this would be the distribution of the hydraulic head in here, and we want to see what that curve looks like and how the flow, the flow is changing as we go from here to here. So we can't do that with the control volume over the whole region. And so what we do is we use a control volume that's smaller, like this, and it, well, call it the width here, call that just the delta X. And this is the delta X, like the kind that we have in calculus, so we can shrink it down. We can make it infinitesimally small, so it becomes just a small little increment in length, and we don't have to worry about then averaging within it because it's so small. So we'll have this this as our control volume, and we can then do a balance on this region. So we could draw it like that in 3D. And it looks like from our sketch that we've got a flow going in and a flow going out here. And we have some recharge coming in. So there's recharge. And this would be Q in. So that looks like the sketch. Let's also draw in the dimensions. So the thickness, what we talked about last time, remember we said that the transmissivity was K times B. I usually use B as the thickness of the aquifer. So this is really spanning the whole thickness. So we'll say that's B. That's delta X. And then this way is delta Y. So those deltas are just like a small little increment of length. So there's my little sketch. Maybe it looks a little better, but I'm going to go up here, and there's what I just drew. And erase it here, so I have a little bit of stuff to draw with. So there's the sketch. So I wrote the deltas a little bit differently here. I'm just going to change that. I'll make it the triangle deltas. But this either way, the delta means a small little increment in length. Okay, so we now want to just do the volume balance on that control volume. And so here it is. I just wrote down the basic balance, right? And that's the same one that we used in the past. So no change there. What I want to do though is write this in terms of a flux. So the Qn, remember capital Q is volumetric flow rate, a volume per time. And we can write that as a flux times in the x direction times the cross-sectional area, which for this, it'll be like that square there, which would be delta x times b. And Q out would be QX, well, let's call this QX in and QX out and delta X and B. Okay, if the volumetric flows are different, then the fluxes would be different as well. And then we have some recharge coming in. It's coming in from above. So that would be R R in. And I'm going to spell it all out. The recharge. Now, these are volumetric flows. So we have to have recharge as a volumetric flow. R, call it, well, I just labeled it R there. Okay, so usually,
Wouldn't it be delta Y?
oh yeah. You know, that, yep, thanks. Okay, so for recharge, this is a flux. So we need to multiply by the cross-sectional area, and it would be this top cross-sectional area, which would be delta X, delta Y. And then we'll have the change in volume stored with time, the rate of change of volume stored with time. Yeah.
How, I see like recharge, is recharge on both sides of that equation?
Now recharge will be going in. We haven't plugged into the equation yet. So we're taking this equation and we're just working out the terms. So this, yeah, and so let me, these Q ins and outs are a little bit different than that. Let's call this Q in, Q out, I don't know, prime. Because the overall Q in will be, well, let's call it Q in low and Q out low. Okay, because the overall Q in is going to be Q in by flow plus R delta X delta Y. Okay, and then Q outflow is just going to be Q out. All right. Okay, so change of volume stored with time. So here's how we're going to do that. We're going to have the change in volume stored per area per change in head. And then I'm going to multiply by change in head, change of time. And I'm going to multiply by delta X, delta Y. Okay, so A in this case, let me just draw our cube here. So this is A. Okay, so I wrote, and the way to think about this is this A is the same as that. So those two cancel out. And that delta H is the same as that delta H, so those two cancel out. And you get delta change in volume stored for time. Okay, so this, it cancels out to be that. Okay, everybody good with that? So the reason though that I do it is because, I don't know, recognize that? Anybody recognize that? Last class? Check back your notes. The change in volume stored per area per change per drop in head. Yeah, so that's the storativity. And the change in head with time, that's just like the rate of change of head with time, right? So I can write this like this. Storativity, and then I'm going to write this as a rate. The derivative of H with respect to T. And then I'll have the delta X and delta Y. Okay, good. So now we can substitute. We'll do this one. And going in is Q in from the flow. Plus R delta X delta Y. And Q out from flow plus S. But I said that Q in flow, well, let me write it like this. I'm going to write it as with the flux, QX in delta Y B plus R. Okay, so that's just substituting, doing this substitution. All right, so this is now the volume balance. We started with that, and on this little differential control volume, we go through some stuff that I think is fairly straightforward. We end up with that. It's starting to look a little messy, but it just follows right directly from the volume balance. Okay. So I'm going to keep this one written down there. So it says from Taylor series. Remember Taylor series? Back from like calculus. Yeah. So maybe a little fuzzy. So what Taylor series says, well, this is from Taylor series, but let me just give you the concept. So we're going to do this. We're going to have, we've got the QX in and QX out. Okay, and then delta X. Okay, so the flux is going along, and we've got little control volume that's that big, and we've got this much going in, that much going out, and they're potentially different. do the stuff that's happening in there. So we could plot Q as a function of X. And right here might be that, and then doing that as a function of X. So this would be Q in right there, and that's Q out. Okay, and this is a small little length, so this is going to be linear, right? Because if it's curved, if we take a curve and have a small length of it, it's linear. So that's delta Q. Think of that as delta Q. Just the change of Q from here to here. So Q out is equal to the Q in plus the change of Q over that delta X. So this change here is going to be equal to the slope times the delta X. So delta Q is H. I mean, we could think of it Q. So this little change of Q is equal to this slope times that distance. That's what that is. You can think of it, this is the slope, and you can think of that, that's a delta X, an actual distance. But you can kind of think of it conceptually that delta X cancels out with that. That's also a dx. So those cancel out and give you like a dq here. Okay. So this goes in there. And this is, if you look back in your calculus, well, this is the first term in Taylor series. There's some other stuff that follow, or it follows this in an actual Taylor series, but we're truncating it. But conceptually, it's pretty straightforward. It just means that the flux that's coming out is equal to the flux coming in, plus this increment of flux that is related to this gradient. Okay. So here's Q out, and here's Q in. So what it says is I can take this and put it in there. Okay, remember, this is all this stuff is on the input side, this is on the output side, that's the flux going out. So I can just write it like this. So if I multiply this stuff through, I'm going to write it all out again. Okay. So multiply this out and I get that. So I'm gonna get rid of this now. Okay, it's getting worse, getting even longer, yeah.
I'm confused how you get to rewrite it like that when we're ignoring recharge in this. In what we subbed out for Q out, there's no recharge included in it, so.
We still have recharge, this is the inflow. So we have recharge times the cross-sectional area and as inflow. So we had that from our previous slide. And we haven't changed it.
Okay, so is recharge gonna be represented in the right part of what we wrote through?
Recharge is gonna stick around. It'll be in the final equation. But it's here just from, this all is the flow rate in. And it's this is the flow, the flow in the groundwater going horizontally in, and this is the flow from above going in. And then this all is the flow going out, and that's the change in storage. But what we did here was to write the flow going out in terms of the flow going in and the change in the flow. Okay, and the reason we do that is because we want to get this, we want to start simplifying. This and this are now the same, they're on opposite sides of the equations, so it goes out. The delta x and the delta y, it's there, it's there, it's there. So that all goes out. So that's going to make this thing a lot simpler. All of this stuff now just simplifies to R. And this is GQ dx times B. And this is S H. Okay, so it simplifies down. And I usually write this with this thing on the left side. So, and then, so we're going to divide through by B and rearrange it. Okay, so this is mass conservation. This is the volume balance. We started with, that equation D, the Q in is Q out, right? That stuff. We're still there. This is still that equation applied to this cube. We've just been, fiddling around with it to get it into a different form, into a simpler form. So that's the simpler form. Look simpler, right? Right? Clear as a bell. Okay. So this is a differential equation, and it is based on, it is really just the rule that we have for the mass is conserved over this little control line. This is the recharge divided by the thickness, storativity divided by the thickness. We saw last time that's specific storage. This is how the flux is changing in the X direction. And this is how the hydraulic head changes with time.
So that B is just the vertical height.
The thickness,
Yeah.
yeah. Yeah, we're not considering any changes over the thickness of the aquifer. And this is, so it's uniform. It's, everything's the same over the thickness and that's just, yeah, the thickness. Okay. So. This, I don't know, when people see this for the first time, it may be a bit cryptic. So I asked the question, does this equation make sense? So I don't know. Does it make sense? Here's a way to think about it. So this is how the flux changes with distance. This would be positive, right? The flux is changing, is increasing in the X direction. So this scenario here, it would be positive. And then dH/dt, that's how the head in here changes with time, the rate at which it changes. Whether if that's positive, then it's going up, and if that's negative, it's going down. Okay, so let's just take this, let's parse this out and say, okay, we'll assume that it's steady. So if it's steady, that means that it's not changing with time. So if it's steady, that term is equal to 0. It doesn't change with time. So if that's the case, then dq dx is equal to r over v. Okay, so here's what that means. So if this is positive, then r is coming in like that. And that must mean this is positive. So if this is positive, then this must be bigger than that. Okay, so what this means is if there's recharge, then the flow in the X direction is going to be increasing because of the recharge. Recharge is coming in, that's contributing to the flow. I mean, sure, that makes sense. All right, so let's say there's no recharge. This would be the other case. So if that's the case, and there's a minus sign right there, right? Great. So if we let r is equal to 0, then we just have this with a minus sign right there. So let's say we have a situation like that. There's more flowing out than it's flowing in. There's no recharge. So how could that happen? So we have
Being pumped on.
we have a tank, we have more flow coming out of the tank than we have flow going in. What's happening to the tank?
Being empty.
Water level in the tank is dropping, right?
You're pumping on it.
Somebody saying something in the line?
Oh yeah, I was just saying you're pumping on the aquifer to go over the head in this scenario.
Yeah, so if this is happening, then the water level must be dropping. Because you're taking more out than you're putting in, so you're removing water from storage. So if this is positive, then the water level is, then this is negative. So the water, well, if this is positive, then this must be negative. So you can take the negative dH dt, multiply by minus sign, and have this side be positive. Right? So if that's positive, this side must be positive. And if this side is positive, then dH dt must be negative, which means that the water level is dropping. Okay? So this equation is saying that in absence of recharge, if this is positive, if the dq dx is positive, then we're releasing water from storage and the head must be dropping. And same, we can do the same thing if we have more flow going in than going out. And this is negative, and that must mean that that's positive. If that's positive, then this side is negative. Okay, so that's the way a way to answer the question whether this makes sense. If you add these two together, it's harder to parse it out because they could be offsetting one another. But if you just isolate it, then I think it makes sense that it would work this way. Okay, good with that? All right, I'm going to do one more step. Then we can call it a day. Okay. So let's write this here. This is not really in a form that we like to solve because it's got these two variables in it that are different. So what we're going to do is introduce Darcy's law. Like that. This flux is the same as that flux. So we introduce the flow law, and we substitute that into the volume balance. We get this. We bring a minus sign out. Okay, so this now is the equation that includes the volume balance and Darcy's law. So this has the two laws in it or the two concepts that we said must hold when we have flow through porous media. We have to have conservation of mass, and we have to have this flow law applied. Okay, we can take the minus sign, change the signs over here. This says take the derivative of this stuff. If a hydraulic conductivity is changing spatially, then we need to do it like this. If this is a constant, it comes out. And then we get the derivative of a derivative, which is the second derivative. And this then ends up being the governing equation for the hydraulic heads in an aquifer. Okay, so this is the equation that we'll be working with for the rest of the class. And using the approach that we started with, we'll simplify it in various ways. And that'll give us opportunities to solve it in different ways. But this is going to be kind of at least for flow in one dimension, this is the equation that will be governing what we'll be doing really for much of the rest of the class. Okay, pretty good. I'll see you on Friday.